So, question 21. I gave this, I guess last time in spring 2017, pull with the friction. This is basically my one question that combines a lot of aspects of Newton's law problem solving in the context of having to deal with only one force, not one force, sorry, having to deal with only one object. And having to deal with only one object actually makes things pretty nice. The biggest of which is that you don't have to worry about Newton's third law. When you have multi-block process, a lot of times people forget about Newton's third law and make mistakes there. So this being a one object problem kind of bypasses all of that issue. So with that, let me kind of just start right away. It says, so that's the description. It's being on the horizontal plane, it's being pulled, and and it's giving me the kinetic friction coefficient between the block and the plane. I think I put that in so that this will also be a friction question. Good. So, all right, let me start out with the free body diagram. So the free body diagram of the block, so here's my representation of the block, single dot. I try to make it as simple as possible because a free body diagram is a problem solving tool. You really don't want to complicate it. You want it as simple as possible. And for this, dot is as simple as possible. So I need to draw forces, starting with the forces that I identify as being necessary. And one of them, kind of obvious, oh, this might be blocked by my video, is tension. So I need to draw tension at an angle, T. And once I draw that, then I realize, oh, but that's not the direction that the block is accelerating. Block is accelerating that way. So I must have something that's balancing that upward component. So I must have the downward force of mg. Now, you could easily end there, but there's this odd phrase from the question. It says, assuming that the block remains in contact with the plane, then you should wonder what that means. And what the eventual answer is that if it's remaining in contact, that means that there is normal force. That is not zero. That is positive. So I need to draw normal force. Even though I guess somehow the situation could be set up where normal force almost goes to zero, but that kind of depends on what the value of tension is. And I don't know that normal force is zero yet, so I need to write this down. And writing this down reminds me that the question talks about the friction force. So, so I need to draw friction force. So if the block is accelerating to the right, I must have friction force to the left. That's going to be canceling out some portion of the horizontal component of tension force. Good. So that's the free body diagram. And I think you can stop here for the free body diagram. And let me go through the remainder of the question, part B. I can bring up some of the considerations in that part B. It says find the acceleration of the block, follow the standard strategy, and give your answer in terms of all that. So I've already done the first step in standard strategy, actually. I drew a free body diagram. So that's my step number one. So I need to step number two, which is defining my coordinate axis. And my acceleration is horizontal, so that seems like a reasonable coordinate axis. That's step number two. And I need to step number three, decomposing forces into components. And it looks like I have only one force that needs to be decomposed into x and y component. And I think I am actually given the angle theta up there. Yeah. So let me write down theta so that I can kind of figure out that the x component is t cosine theta and the y component is t sine theta. All right, that's step number four. Finally, step number four, I need to write down the Newton's second law equations. I have one object, 2 dimensions, so I need 2 equations. So my Newton's second law equations are net force in the x direction. So that would be the x component of tension, T cosine theta, minus the friction force is equal to mass times acceleration. And I have the net force in the y direction is equal to normal force plus I have the y component of tension force, Ty or T sine theta, minus mg. And since it's not accelerating in the vertical direction, that's equal to 0. All right, so I have 2 equations. And let me count the unknowns. 1, 2 equations. And then my unknowns are, I know tension, I'm given tension, I think. I don't know friction force, I'm not told that. I'm asked to find the acceleration, so I don't know that. And I don't know normal force. 3 equations, so that means I need 1 more equation. And this is where I hope you kind of think through what forces you are given and how you can get information about that particular force. Because one thing that I haven't made use of is that this is a friction force. And there's actually a formula for kinetic friction force. So let me write that down. The formula for kinetic friction force is the coefficient of friction times normal force. So looking at this here, okay, this last equation didn't introduce anything we didn't know. We were actually told what the numerical value of, we aren't. Okay, so I need to keep that. So yeah, so I now have the 3rd equation and no new unknowns. So 3 equations, 3 unknowns ought to be solvable. Let me solve that. So one thing I do know is that I want to get the acceleration of the block at the end, which means what I make sure not to do is I solve for acceleration right now. Instead, what I need to be doing is solving for normal force and frictional force. So, all right, let me solve equation 3 for normal force. Then I have normal force is equal to the equal to the friction force minus mu. So that's 3 prime. So let me take this take this expression for n that I solved and plug it into equation 2 to get this expression. So n, let me write it down. The friction force over mu plus T sine theta minus mg is equal to 0. I'm trying to solve for acceleration. I don't know the friction force. So what I should do is I should solve this for friction force. Let me just do this in my head. That's going to be mu times mg minus T sine theta. Plug that into the equation 1. Let me call this equation 2 prime. So from equation 1 and 2 prime, this is what we end up getting. T cosine theta minus that complicated expression for friction force, mu mg minus T sine theta is equal to mass times acceleration. So all I need to do is to solve for acceleration. As I do that, I can simplify this a little bit, so I will. I'm just gonna kind of collect like terms, but you don't have to. I'm doing it for the fun of it. So let me solve this for acceleration here. One term I'm going to pull out is all the terms dealing with the tension. So I'm going to have tension over m, and I have things inside the parenthesis. Cosine theta, that's this one. And I need to be careful with this one here. It's minus mu times minus sine theta. So it's plus mu sine theta. And what this really means is this is actually vertical component of tension that's helping you reduce the friction force by reducing this normal force here, because this amount of tension force helps you reduce the normal force needed. All right, I did that. I have one more term here. That's going to be minus mu m, m cancels out, minus mu g. And what this is it's the friction. It's whenever you have larger friction, that's going to be slowing down your acceleration for a particular amount of tension and at a particular angle that you're going to apply. So yeah, that's the answer here. Acceleration is that. And once you have this analytical expression, that becomes a tool to answer other questions. That's what question C is about. It's getting you to optimize this with respect to theta. You can do that on your own or ask Cadres to do it in the study group. And the D is actually the harder one. You kind of have to redo the whole question from scratch, but I'm frankly out of time. So I'll leave that for some future date, and I will have time to cover that.